Alright, AP Physics 1 students. So you watched those videos, which were pretty cool, showing that anytime there's sort of relative motion between a magnet and a wire, we're going to get a current, even though there's no battery. That's pretty weird. So let's investigate what's going on here. So we're going to take the example of moving a conductor through a magnetic field. So let's draw a picture of what's happening. Let's say we're looking at a top-down view. We're looking down at this. Right? And here's this bar, which is a slab of metal, some sort of conductor of length L. We're going to move it to the right at a velocity v. Inside a magnetic field, which is going to be pointing, in this case, into the page. So we're looking down at it. Imagine we have a large laboratory magnet, and the field is pointing into the table. And on the table, we've got this wire, this conductor. We're going to move it to the right in this external magnetic field. All right, so what's happening here? Well, let's visualize the protons and electrons inside. Because it is a conductor, the charges are free to move, and we're going to go with our usual conventional current. So we're going to imagine the motion of protons, even though we know in reality it's actually electrons. Okay, so look what we have. We have all these mobile protons, is a neutral object, these mobile protons inside a conductor, and the protons are moving to the right inside the magnetic field. They're going to experience a magnetic force, right? All right, let's do our right-hand rule. This is going to be the pointing one. So the charges are moving to the right, field is into the page, go ahead and do it. Which way are we getting for the magnetic force on these moving protons, the positive charges? They're going to be forced to the top of the page, right? Not say up or down, to the top of the page or the far end of this conductor. And so little by little, these protons are going to start to drift that way, right? And they're going to start to collect more and more positive charge collecting over here, leaving behind negative charge. There's now an absence of positive charge. So we're getting a separation of charge, positive charge collecting on the far end, negative charge collecting at the near end. Let's draw this in another perspective, right? So without all those charges sort of muddying up the picture, here's the positive end, because the positive charge protons are collecting there. They're leaving behind negative charge below at the bottom end, or the end towards us, and the length is L. And so what we're getting is a separation of charge. Anytime there's a positive and negative separated, they're going to create another type of field. What sort of field is that? That's an electric field. Yeah. So go ahead and draw the electric field inside the conductor from positive to negative, right? We went over the rules just last class. It's going to point this way. It's almost like it's a uniform electric field. Like these are almost oppositely charged parallel plates. They're creating an electric field, which means that this is going to be the high potential, this is going to be the low potential. There is now a potential difference or a voltage from one end to the other. Let's look at the implications on one of these protons. Maybe this one over here is sort of caught in the middle, about to be forced this way. So we already know from the motion of this proton to the right inside the magnetic field, it feels a magnetic force to the top of the page or away from us, this end, that's why they're collecting over there. But now, as they get more and more separation of charge, we get more and more of a field here. This positive charge will feel a force from the field, the electric field, I should say. And which way is that direction? Well, we just went over the rules last class. We know that positive charges follow field lines. This is going to feel an electrostatic force to the bottom of the page or towards us. And as more and more charge collects here, as more and more potential difference occurs, as more and more of a field builds up, this force is going to get larger and larger until these forces balance out. When they balance out, that's when the charges stop moving. That's when we get our final separation of charge, positive there, negative there, and the ones in the middle, they're caught in the middle because the forces are balanced out. Well, let's put some equations in here and see what happens. For the electrostatic force, we want the force in terms of the field. So we should remember that, of course, it's going to be Q times Z. It's not going to be Coulomb's law, KQ1, Q2 over R squared, because we're not talking about multiple point charges, but only one point charge, right? So it's just in terms of the field. What about for magnetic force? Which force equation is that? Is that ILB sine theta or QVB sine theta? I mean, it should be pretty obvious, right? We're looking at a point charge. It's going to be QVB sine theta. If you're still confused about that, you really need to go back and review your equations and look what's in there, right? It's got a charge in there, so we got a point charge there. Things are going well. What about theta? Ooh. Where's theta measured? It's always between the two previous vectors, so velocity and field. So velocity is to the right, field is into the page. What angle is that? That's 90 degrees, like it almost always is, and sine 90 we know is 1. And we have a Q there and a Q there. What's going to happen? They're going to cancel, so we have E equals VB. Well, this should look awfully familiar. You might recall this is how we got the speed for the velocity selector. I'm still not going to box it in. It doesn't make it a new equation. It's just, it happens again. Anytime the electrostatic force and magnetic force on a point charge are equal. Okay. But what's interesting is, as I mentioned before, there's almost like the positive plate and the negative plate of oppositely charged parallel plates, and we have an equation for electric field in terms of the voltage, the potential difference between them. Disregarding the sign, it's negative, it's delta V over delta D, or in this case, that's the length of the conductor, right? The potential difference over the distance between the plates. So we're just going to set these two equal to each other. I'm going to drop delta V over L in here. Now at this point I want to make sure we're very, very clear. What does this V stand for? Yeah, that's speed. That's how fast the bar is moving. What's this V? That's potential difference, right? The voltage between the ends. And that can be kind of confusing, but I want to make sure we're very, very clear. Make sure you're writing your V's properly, right? This V has little lines on top, and it's a capital V. There's a lowercase v. It can be kind of confusing. And so, you know what? We're going to replace delta V with another term. Remember, we used another term back in circuits of EMF. And so that's what's happening here. We're developing an EMF from one end to the other. But that's also a little confusing, right? Because this capital script E is EMF. What's this capital E for? That's electric field. So if you've been writing EMF as capital E, you've got to stop that. They're not the same thing. This should be a script capital E. Otherwise, you can be very, very confused, right? Okay. So this is EMF over L equals VB. We're going to solve this for EMF. And for whatever reason, we always write it as BLV. I don't know if it's because it's alphabetical. And this is what we're going to box in. So this is what we have here. By moving a conductor through a magnetic field, we create a voltage, an EMF, from one end to the other. And then if this were connected to something, it could actually drive motion of charges as if it were a battery. So we call this motional EMF. Not emotional EMF. It's got nothing to do with your feelings. It's motional EMF. It only happens because we're moving the conductor. We produce an EMF, a voltage, from one end to the other. B is an external magnetic field, which I wrote over here. I don't have to write it every single time. I want to make sure we're very clear that this is a field produced by something that's not even in the picture. We don't care what it is. V is just the speed of the conductor, nothing fancy there. L, let's be careful, that's the length of the conductor that cuts across field lines. I want to make sure we know which dimension we're talking about. That's this length here, not this length here, right? This is the length that's cutting across field lines. This one is just sort of parallel, so it's not really, there's no length to it that's cutting across, okay? I'll make sure we just know how to use it. Okay, now I said the whole point is that now that there's a positive end and a negative end, let's do something with it. Let's redraw it and put it on top of some conducting wires. Again, we're looking down at it. So these are conducting wires. We put our conductor on top of them inside a magnetic field. As we just showed, we can get a positive end here, a negative end here. Now, let's connect these two ends through maybe a resistor. Now, the protons that are collected here see an escape route. They can complete the circuit and go around, and we're actually going to create a current, which is what you saw in the videos there. Create a little bit of a current. Okay, so let's go to problem 8 here and see, oh, there's the exact same picture we just drew. Okay, so pause the video, try solving problem 8, then come back to see how I solve it. Okay, so find the induced current in the rod. Should be real simple here. We're going to start with Ohm's law, which we can write as delta V equals IR, but I'm going to write as EMF equals IR because we're using EMF in our previous equation. How do we find EMF? Well, it's a motional EMF because we're moving this conductor inside the magnetic field, so it's BLV, and it's not too difficult here. Certainly you could find EMF if you'd like to. I think we get 0.405 volts, but we just want to put the equations together. We get BLV over R, put the numbers in, and it's not difficult math here. We should be getting 0.675 amps. Nothing fancy. Part B, we want to find the power generated in the resistor. And it is a circuit, right? There's the positive end, there's the negative end, charges are moving around. We got a continuous flow of charge. And we can pick any one of your favorite power equations. It could be I squared R or delta V squared over R, which is, in this case, EMF squared over R. But I particularly like I delta V because when we write it in terms of EMF, this is power equals I times EMF. And this equation is just easy as pie. Yeah, okay. Anyway, so we can put the numbers in again. If you found the EMF from before, it was 0.405 volts, or if you want to do I squared R, we found the current. Any way you do it, you should be getting 0.273 watts. Again, nothing fancy here, just reminding us how we did this back in circuits. Alright, now let's go on to problem 9, which uses the same picture, but it's from a different perspective. Just read this for a second. Don't pause the video yet. Let's talk about it. Okay, so the idea here is we've shifted perspectives. This was about the velocity of the bar, but now we're looking at the force we're applying, because obviously if we're moving it to the right, we have to apply a force to the right to get it to move, and the question is how much power is required for us to maintain that force. So this over here is electrical power. We're not talking about that. We're talking about mechanical power. So we want to think back to how we had originally done mechanical power earlier on in the year. Remember, power is the rate of work being done, the rate of exchange of energy, and if you think about it in terms of the force, we had that other equation, FV bar cosine theta. Now, I know the book doesn't always put the bar there, but we should. It is an average speed, and sometimes other sources don't even put the cosine theta, but the cosine theta is an important part of this. Okay, so where's this force? Well, let's take it from the perspective of the bar moving, right? So we know that this end is positive, this end is negative, and that's driving charges around in this direction, and we just follow those charges around. Now the charge is moving this way inside the conductor. Let's look at the conductor itself. So here's this conductor. It's like a wire with a current inside this external magnetic field. It's going to experience a magnetic force, isn't it, right? All right, let's go ahead and do our right-hand rule for the direction of the force on this wire. Be very careful finding the force on the wire. Is this the pointing or the grabbing? This is the pointing, okay? So we point in the direction of the motion and charge. That's the top of the page or away from us. Our field is pointing into the page, and when we stick your thumb out, we should be getting the magnetic force on this wire, this conductor, is to the left. Oh, we're pulling to the right, and the force from the field is to the left. They are opposing each other, right? Here's the force that you are applying, opposed by the magnetic force, which should make sense, right? Because if we pull on this bar and we just let go, and it would just continue to create current, that doesn't make sense. The universe isn't going to allow that. The universe isn't going to allow you to just get something from nothing, right? We have to be able to keep doing something, so we have to keep pulling, because otherwise the magnetic force wins. And it does say we're moving at a constant speed, right? So we know that the force that you supply, right, is exactly equal to the force, magnetic force on the wire, on the conductor. All right, so what's the equation for this magnetic force? Is that QVB sine theta or ILB sine theta? Well, hopefully you see there is no moving point charge here. This is definitely ILB sine theta. Oh, but wait a second. We have two different thetas, and you know what? These aren't even the same theta. Let's look at this one first. Where's theta measured? Well, as I mentioned just before, theta is always the angle between the two previous vectors. That's between L and B, which I know L is kind of weird, but that's the motion of charges, right? And so these charges are moving to the top of the page. The field is into the page. What angle is that? That's 90 degrees. Sine 90 is 1, so it's not going to matter. Where's this theta measured? Well, what are the two previous vectors? It's force and velocity. We're forcing it to the right. It's moving to the right. What angle is that? That's 0 degrees. And oh, what's cosine 0? That's 1 also. So isn't that nice? Let's be very careful though. These two thetas are just not the same thing, but they both go to 1 as we put them in. Okay, so go ahead and combine the equations, put your numbers in, let's calculate. Okay, you should have gotten 0.273 watts. That's interesting, isn't it? Wait a second. Huh. We are getting the exact same answer for problem 8 and problem 9. Why is that happening? Well, I sort of gave it away before by saying that we had to keep pulling, right? This is kind of interesting. We've got charges moving around here, producing power in this resistor, and yet, where's the battery? There is no battery. There is no source of voltage, but something's got to drive charges around. Where's the battery? It's you, isn't it, right? If you have to keep pulling, you have to keep applying this amount of power. You're using up your energy at a rate of 0.273 joules per second. It's coming out in the resistor as 0.273 joules per second. You are the source of voltage by continuing to apply a force. Because again, when you let go, if you were to let go of this, your force goes away, the magnetic force pulls back, it would slow the bar down, and that would take the energy away, because you can't get something for nothing. You are actually, in effect, the source of voltage. That's pretty cool. Now, of course, you should have suspected this, because let's look at the equations, right? The force here is ILB. So we put ILB in here for the force. Not working. Here we are, right? And I'm going to drop the bar part of it. And I'm just going to rearrange a little bit. This is I times BLV. And wait a second, BLV, that's EMF, isn't it? And so, of course, we have to get the same thing, because mathematically, it's the exact same equation. Of course it is. Okay, now at this point, you might be getting a little bit confused. Alright, so in your notes, I want you to draw these two pictures. Pause the video, draw these as carefully as you can. Okay, so the question is, what's the difference between these two pictures? I really want you to think about this. Pause the video, write down what you can write down about what's different about them and how you know you're looking at two different situations. Okay, so clearly both have a wire with current and a magnetic field shown, but what's the difference? Well, here, all the field lines are evenly spaced, and here they're closer together and spread apart, closer together, spread apart, and here they're all pointing the same way, and here they're pointing one way, pointing a different way. So what's the real difference? Well, hopefully you recognize that picture 1, this is the field created or produced by the wire. If you were to do your right-hand rule, you'd feel your fingers hitting the paper on the right-hand side, poking up out of the paper on the left-hand side. Opposite directions, right? Going around and around the wire. But what's going on over here? This is a wire sitting in someone else's field. What's the difference? Well, here again, we've got field pointing in different directions, and it has to because the field lines circle the wire. Here they're all pointing the same way. Here they're spaced evenly. Here they're spaced in such a way that as they spread apart, the farther they get. And you have to be able to identify the picture you're looking at. Otherwise, you're going to be very confused and you're going to interpret them incorrectly. So this is the field produced by it. This wire is going to feel a force.